So this is a relative motion problem. Anytime you have one motion like riding on top of another motion, where you're describing one in terms of how it relates to the first one, like you do here, the motion of the car, we're given in terms of the ship, and the ship is also moving. So those are always going to be relative motion problems. So we know we're going to have the acceleration of the car relative to the ground equal to the acceleration of the car relative to the ship plus the acceleration of the ship relative to the ground. Okay, so I'll first do the acceleration of the car relative to the ship. We're given the velocity vector in terms of y. So v is equal to 5y squared negative, was that cosine of y? Okay, and so the acceleration is dv dy times dy dt, and that's dv dy times the y component of the velocity. So that is, take the derivative of v with respect to y, and you get 10y, and then 10 sine y. That's dv dy, and then multiply it by the scalar y component. So negative 10 cosine y. And you get a value of negative 100 y cosine y and negative 100 sine y cosine y. Okay, so that's the acceleration of the car with respect to the ship. And now for the acceleration of the ship with respect to the ground, the velocity is 10x 2x. So the acceleration of the ship with respect to the ground is dv dx dx dt, which is dv dx times the x component of the velocity. So, notice that because of the variables that each of these depended on, we ended up with a different component of the velocity that we're multiplying by in the chain rule. That's an important thing to follow. And so dv dx is 10, 2, and the x component of v is 10x. So you get 100x, 20x. And so now finally, relative motion equations say the acceleration of the car with respect to the ground is equal to the acceleration of the car with respect to the ship plus the acceleration of the ship with respect to the ground And so that is negative 100 y cosine y plus 100x, and then negative 100 sine y cosine y plus 20x. So that's a function, that's the acceleration of the car with respect to the ground is a function of x and y. And now we're done with the right side of Newton's second law. So the left side, draw a free body diagram of the car. This is, well, it's a function, so it's like there's nothing to solve. It's just like if you are given a location of the ship, you can plug the x and y values in and it'll give you the acceleration.
I didn't know if it was somewhere you can set up the matrix and have like two by two because you have two unknowns in between, so like if you.
Oh, no, it's a function. So those chain rule problems, you're always either solving for a function of x or y or z, or else you're given specific values of x, y, and z and asked to come up with a number. So I could have said when you're 150 meters x, 200 meters y from port, plug those in and come up with the acceleration, and this would have given it to you. Yep.
Can we, he came up with an idea where you just add the velocities and then take the derivative. That's what I did. Yeah, as long as you do the full chain.
You have to do the full chain rule.
Yeah.
Yep.
Right. That's fine.
But then you come out with something that then you can separate out into this same thing, right? It looks the same, doesn't it? It doesn't?
Well, there are a couple of like terms that are the same, like the negative 100 y equals y and the 100x.
Different concepts.
If you do the partial v of x times
Mhm.
partial x of t, then you would just use the x components. But when I first did it, I used the x and y components when I added t
Mm-hmm.
and added a bunch of extra variables.
So you would have to do that. If you did it that way, you'd have to do, so the acceleration would be dv dx times dx dt plus dv dy times dy dt. You did it that way? Yeah, that works. Those should be the same thing, yeah.
But the dx dt, if you add the velocity vector,
Mhm.
is 5y squared plus 10x, and then 2x minus 10 both sides of y.
Okay.
If you add them up first. So then you
Uh-huh.
are multiplying 5y squared plus x to the partial derivative with respect to x. But it works out the same if you just use the x value.
Well, let's talk about it after class if any of you have time. Yeah, it should come out the same. Right. Yeah. All right. So what forces? We're looking at this in the plane of the deck of the ship. What forces are acting on the car? Yep. So there's a force downward of, I think I said 2 kilograms. So 19.62 newtons down. And then there's a force on the car by the ship. And Newton's second law then says FCS X, Y, and Z plus 0, 0, negative 19.62 is equal to the mass of the car times that crazy function and I only have X and Y components here. You have to have a Z component to add these. And okay, so you end up with the force on the car by the ship equal to negative 200 Y cosine Y plus 200 X minus 200 sine Y cosine Y plus 40X and then positive 19.62. Yep. Question?
In your original question, did you ask the force of the car relative to the ship? So would it just be the acceleration of the car relative to the ship?
No. Okay. So yeah, that's like an important point. So you can't use any of the laws of any of the equations of motion, Newton's second law or rotational Newton's second law, in non-inertial coordinate systems. And so really, in a way, it's because forces don't change when they're applied in a non-inertial coordinate system. Like a force is either 50 newtons or it isn't. It doesn't matter who's measuring it, you know. Someone could stick a force measurement device in as they accelerate by, and they'll still measure the force the same, you know. The reason the laws of physics don't work in inertial coordinate systems is because you get the same force that you would in an inertial coordinate system, but you get a different acceleration because, well, of this stuff, of the relative motion stuff. And so we have to make these corrections so that the forces do match up with the accelerations. So basically, forces are always, accelerations you have to worry about, like, was this acceleration measured in an inertial or non-inertial? Forces, you don't have to worry about that. A force is a force, of course. Yep.
I'm a little bit unclear on how you tell me relative motion.
Okay, so look for problems where motions are piggybacked on top of each other. So someone inside a moving car does something, you know, someone inside a moving vehicle does something that you have to calculate. Someone on a moving ship does something, or with circular motion, you could have a circular motion where the axis is also moving according to some function. In all of those cases, there's one motion that's happening, that's doing its thing to somebody who's observing on another moving thing. Okay, so that's what you look for. The shortest, easiest, quickest, and dirtiest answer, this isn't always true, but it's probably fair to assume that in this material, if you have any two motions, you're probably going to have to deal with relative motion. Any other questions about this? So yeah, the challenge for the test tomorrow is recognize when you have to use relative motion and be able to do that, recognize when you have to use the chain rule and be able to do that. And third, recognize when you have to use circular motion equations. That part's not too hard if it's moving in a circle. But know how to use those. Anything else is really just applications of the same differential equations that we did for the last test. Sure. On kinematics? Yeah. Is that in here too, Seth? Is this yours? Oh, is that in here? Just earlier? Okay. Okay. So the practice problems on kinematics. Number 4. So you have an object that is moving along the path y equals sine x. So it's following this path, and it says it's moving in the direction of positive, like as x is increasing. So it's going this way instead of the other way. The speed is constant at 3 meters per second. So the parameterization of an object is x sine x. And we want to figure out the velocity vector as a function of x. Then we want to use this to figure out the velocity vector when x is equal to 0. Then the acceleration as a function of x. And the acceleration when x is equal to 0. All right, so to figure out the velocity vector, that's the speed times a unit vector tangent to the path. We can come up with a non-unit vector that's in the direction of the path by taking the derivative of the position with respect to the parameter, whatever variable you have. So dp dx, so that's 1 cosine of x. But that's not a unit vector. And so if you multiplied the speed of 3 meters per second times this vector, you'd get a vector that was in the right direction. It just wouldn't have a magnitude of 3 meters per second. So it would be in the right direction as the velocity, but the magnitude would be wrong. So that's why we need to find the unit vector. So the magnitude of this vector is 1 squared plus cosine squared. And so the unit vector is 1 over this thing, 1 plus cosine squared x. That's not a constant, but I'm just setting myself up for a lot of writing that I'm going to have to do here. And then the y component is cosine of x over 1 plus cosine squared x. All right, so then the velocity vector is the speed times this, so 3 over 1 plus cosine squared x and 3 cosine x over 1 plus cosine squared x. Okay? So when x is equal to 0, so v evaluated when x is equal to 0, cosine of 0 is 1, so we have square root of 2, so this is 3 over root 2, and this is also 3 over root 2. Any questions about that part? Okay, so now the acceleration. The acceleration is equal to the derivative of the velocity with respect to x times dx dt. And dx dt is the x component of the velocity, so that's dv dx times vx. Okay, so this is v. So v is equal to 3 times 1 plus cosine squared x to the minus 1/2, and then 3 cosine x times 1 plus cosine squared x to the minus 1/2. So dv dx is minus well, let's say, okay, so it's 3 times minus 1/2 times 1 plus cosine squared x to the minus 3/2 times 2 cosine x times negative sine x. That's x, that's the easy one. And then the second one is negative 3 sine x times 1 plus cosine squared x to the minus 1/2 plus 3 cosine x times negative 1/2 times 1 plus cosine squared x to the minus 3/2 times 2 cosine x times minus sine x. I'd say probability of 0.06 that that's right. And so acceleration is this whole thing times, you know, this whole thing times the x component of the velocity, which is 3 times 1 plus cosine squared x to the minus 1/2. So you get this big expression for the acceleration vector. I'm sure it simplifies quite a bit, but still probably looks pretty ugly. And then plug in 0 for x, and that'll give you the acceleration when x is equal to 0. Which I think is probably 0 because it's a, yeah, and also that sine curve is at an inflection point when x is equal to 0. So it's not. But yeah, I mean, I guess, right. So when x is equal to 0, all the signs are equal to 0. So you have a 0. So the first component here is 0. This is 0. This is 0. So yeah, the acceleration is equal to 0. Any other questions about that one? So it doesn't, I don't think it makes any sense to start new stuff right now. So let's do something else. Yeah. So what's another one you'd like to see, or what type of problem? Number 2 on kinetics. Oh, yeah. Okay, so this is the one with the pulley system. We rigged this system up in office hours the other day, and so you could feel it. Come on in and you can see, like, you put a 1 kilogram weight on one pulley, it feels really heavy. Rig up a system like this, and you can tell that it's half as heavy. So you have a 150 kilogram mass coming from this hanging pulley, and then a single cable goes from here around the pulley up around this pulley, and then, whoops, you have another 100 kilogram pulley there, 100 kilogram mass there. And we want to know first, what's the acceleration vector of the 150? And second, we want to know what's the position vector as a function of time given some boundary conditions. So we'll get to that in a second. And I didn't read what the boundary conditions are, but I knew that, I expect those things to be boundary conditions. And the reason that I expect that is, you might think because I wrote the problem, but no, it's not that. I don't remember, 5 minutes ago. But the reason is, if you're starting with acceleration and integrating to get position, you know that you're going to have constants of integration. So to come up with to be able to do that, you have to be given boundary conditions. So the acceleration of the 150. Let's start with free body diagrams of both of these. So free body diagram of the 150. And I'm going to include all the stuff that's hanging. So what forces are acting? We know there's weight, so that's 150 times 9.81, so 1471.5. And then the only place that there's contact with this boundary is the cable tension in two places. And then the free body diagram of the 100 kilogram mass. There's a downward force of 981 and an upward force of T. And I know that these cable tensions are all the same because it's the same cable moving through these pulleys. One of the things, so the assumption that we're making for that to be true is that these are frictionless and also that they are massless. If they had mass, then there would be some moment required to cause them to rotate, and that would come into it. We'll be able to do problems like that when we start talking about linkages. Okay, so Newton's second law for the 150 says 0 2t plus 0 negative 1471.5 is equal to the mass times the acceleration. Do we know anything about the acceleration, the magnitude, or the direction? Yeah, we know everything's going to happen in the y direction, so let's just call this 0 a150. And then Newton's second law for the 100 kilogram mass says 0t plus 0 negative 981 is equal to the mass times the acceleration of this one. And we know the same thing about this. It's going to be vertical acceleration, nothing side to side, so I'll just call this 0 a100. All right, so we have, we have 4 equations, but you can see right away that 2 are going to be useless. The x equations both just say 0 is equal to 0. Question? That 2t is what's going to cause that, but we are going to have to put one more geometric constraint in. So I was just getting to that, like, is there any way to sort of see what's coming down the road at us? Well, let's count the variables. We have the variable t, and we have the variable a150 and the variable a100. So we have 3 variables, but only 2 useful equations. So we know that we need another equation relating these variables in some way. We need another equation that doesn't add any more variables. So where's that going to come from? Well, that's going to come from the fact that this block and this block move in a prescribed way. Okay, so if the 100 kilogram block moves down an inch, how far up does the 150 move? Half an inch. And the reason is that, so think of adding 1 inch to the distance from this pulley contact to where the 100 kilogram mass is. Okay, where does that 1 inch come from? half an inch of it comes from the distance from here to here, and the other half inch comes from the distance from here to here. Okay, so the distance, so adding distance to this part of the, like this path of the cable, removes half that much distance from here and half as much from here. It's dividing that distance up into two pieces. And it's not just the position. If you add the position as a function of time, well, derivative is a linear operator. So if the position here, or think of the displacement of this, is twice as much down as the displacement of this is up, then also the velocity of this down is twice as much as the velocity of this up. And take another derivative, and the acceleration of this downward is twice as much as the acceleration of this up. Okay. So what you get is your last equation says negative A100 is equal to 2A150. Okay. So if A150 accelerates upwards half an inch, A100 is downward 1 inch. And so now you can set up your system of equations. The first one says 2t minus 150 A150 is equal to 147 or 1471.5. The second one says t minus 100 A100 is equal to 981. The third one says negative A100 minus 2A150 is equal to 0. And so if you go T, A100, A150, and then the constant, your augmented matrix looks like this. 2, 0, minus 150, 1471.5, and then 1, minus 100, 0, 981, and then 0, minus 1, minus 2, 0. Do reduced row echelon form on that matrix, and it should give you A150. I think that's what you're looking for. Yep.
The negative A100 equals 2A150. That's something to do with the Pulley masses, right?
That's right. That's right. Yeah, that's just a geometric thing. So no matter what the masses were, as long as that cable doesn't fold, you know, that relationship has to stay. Any questions about that? Okay. Well, if you come to office hours, we'll hook up a thing. All of you can stand on a platform, and I'll lift it up with my pinky. Actually, our pulleys probably aren't strong enough for that, but otherwise I would do that. Yeah. It's that physics string. It's not the strongest stuff.